The Hyndmans Creek Bridge, located on Comboyne Road, underwent a significant transformation with the replacement of the old timber structure that had served the region since its construction around 1955. This timber bridge had long outlived its service life, presenting increasing safety concerns due to its age and deteriorating condition. In July 2017, a 10-day shutdown of Comboyne Road facilitated the replacement of the bridge with a modern prefabricated concrete structure, marking a pivotal upgrade to local infrastructure. The existing timber bridge, which had been a critical crossing point for decades, was no longer able to meet the demands of modern traffic. Over the years, wear and tear had compromised its structural integrity, and maintenance costs had become increasingly prohibitive. The need for a new bridge was clear, and a decision was made to replace the outdated timber structure with a prefabricated concrete bridge. The concrete design was chosen for its durability, strength, and minimal maintenance needs, which would ensure a safer and more reliable crossing for years to come. The replacement project took place during a 10-day shutdown of Comboyne Road in July 2017. During this period, crews worked intensively to demolish the old timber bridge and construct the new concrete structure. The process included the careful removal of the timber bridge, which required skillful coordination to minimize disruption and maintain safety. Once the old bridge was removed, the prefabricated concrete sections were transported to the site and assembled. This prefabrication method significantly reduced construction time and minimized the impact on local traffic. The new bridge was designed to handle modern traffic loads, including larger vehicles, and was built with materials that are more resistant to the elements, ensuring a longer lifespan compared to the previous timber structure. The prefabricated concrete bridge also boasts improved safety features, such as wider lanes and better alignment, enhancing both driver and pedestrian safety. The Billings Bypass Yellowstone River Bridge is a vital infrastructure project completed in 2022 as part of the larger Billings Bypass project in Montana. Constructed by Wadsworth Brothers Construction, the bridge serves as a key link in improving transportation and accessibility between Lockwood and Billings Heights, two communities located on opposite sides of the Yellowstone River. The Billings Bypass itself is a multi-phase project designed to alleviate congestion within the city of Billings by providing an alternative route for traffic traveling around the city rather than through it. This bypass is crucial for enhancing the efficiency of freight movement, especially given Billings' position as a transportation hub in the region, and it also supports local residents by reducing travel times and traffic on congested city roads. The Yellowstone River Bridge spans one of Montana's most iconic rivers, requiring advanced engineering to ensure both functionality and environmental sensitivity. The bridge is designed to handle increased traffic volumes, particularly heavy trucks, which are common in this region due to the area's strong agricultural and industrial base. With its strategic location, the bridge facilitates smoother travel and encourages growth by connecting key areas of Billings that were previously more isolated due to the geographical barrier posed by the Yellowstone River. Construction of the bridge required careful consideration of the river's natural ecosystem. Montana Department of Transportation, MDT, worked in partnership with environmental agencies to ensure minimal disruption to local wildlife and aquatic life during the construction phase. This attention to environmental impact reflects MDT's commitment to sustainable development while enhancing the state's transportation network. The erection of box girder segments, especially by VSL Indonesia, is a specialized process used in the construction of complex infrastructure projects such as bridges and viaducts. Box girders are widely recognized for their strength and efficiency in supporting large spans with minimal material. The box girder segments, which are hollow rectangular structures, offer excellent resistance to bending and torsion, making them ideal for supporting roadways and railways. VSL Indonesia, a subsidiary of VSL International, specializes in post-tensioning and heavy lifting solutions, playing a key role in the Indonesian infrastructure sector. Their approach to box girder segment erection involves both advanced technology and refined techniques to meet the specific needs of each project. They use segmental construction methods where the box girder segments are prefabricated in sections and then transported to the site for assembly. The segments are aligned and connected using post-tensioning systems, which introduce compressive forces that hold the segments together and enhance the structure's stability. VSL Indonesia employs a range of equipment in this process, including launching gantries and overhead cranes, which enable precise positioning and alignment of segments. The company also uses specialized lifting frames to transport and install the heavy box girder sections, especially when working over water or inaccessible areas. The launching gantries allow for segments to be moved horizontally or vertically into position, which is especially beneficial for bridge construction over busy highways or waterways where minimal disruption is required. A critical aspect of VSL's method is its focus on safety and precision. The use of post-tensioning is crucial in ensuring that the assembled box girder segments can bear significant loads immediately upon installation, reducing the construction time and enhancing safety. The construction of the Berg River Bridge at Valdivia Estate, officially opened on June 21, 2018, marks a significant infrastructure advancement for the Drakenstein municipality. Spanning 400 meters, with an additional 1.2 kilometers of connecting roads, this bridge is the first private bridge of its scale in South Africa. It was designed to connect the Valdivia Estate with the R45 Simondium Road, drastically reducing travel times to key locations. It now takes only 30 minutes to reach Cape Town International Airport, 16 minutes to Stellenbosch, and just 3 minutes to Paarl Main Road. The construction process took 2 years, involving extensive planning and engineering to ensure its resilience and longevity, costing approximately R100 million. This investment highlights the commitment to improving accessibility and mobility for residents and the surrounding community. At the opening event, Martin Venter, founder and CEO of Valdivia Estate, emphasized that the bridge represents human progress and extends its benefits beyond the estate's residents to the wider Drakenstein community. The bridge project was completed with advanced engineering practices, focusing on environmental sustainability and minimizing disruption to the natural surroundings. On January 4, 2018, a significant construction milestone was achieved with the launching of bridge beams, comprising T-beam and U-beam, near Jalan Teknologi 3/6 in Kota Damansara, Malaysia. This event was an essential part of the structural progress for a critical road infrastructure project aimed at enhancing connectivity and reducing traffic congestion in the bustling area of Kota Damansara, which is a major suburb of Petaling Jaya in the Klang Valley region. The installation process involved the use of 2 types of beams, T-beams and U-beams. T-beams, recognized for their T-shaped cross-section, are often used in bridge construction for their capability to support heavy loads while requiring less material, making them both cost-effective and structurally efficient. U-beams, with their U-shaped cross-section, add stability and enable more accessible fitting with bridge decks and other construction elements. Together, these beams form the backbone of the bridge structure, providing robust support for the future road surface and ensuring long-term stability for high-volume traffic. The launching process, commonly referred to as beam launching, involves a series of meticulous steps to place the beams accurately on the bridge piers. Given the weight and dimensions of these beams, heavy machinery, such as cranes or specialized launching gantries, is employed to lift, position, and secure them. Beam launching is a high-precision activity, as incorrect placement or alignment can compromise the entire bridge structure, resulting in costly adjustments or, worse, structural vulnerabilities. The operation on January 4 was conducted by a team of engineers, crane operators, and construction specialists who collaborated to ensure the beams were set in place with optimal precision. This event was not only a technical accomplishment, but also a pivotal step toward advancing road infrastructure in Kota Damansara. By alleviating traffic bottlenecks and improving accessibility, the bridge near Jalan Teknologi 3/6 would contribute to the development of the surrounding area, accommodating the increasing transportation demands and supporting local economic growth. The relocation of the Rosbruck Bridge represents a monumental engineering operation that underscores the complexity of modern infrastructure projects. Situated in France, the Rosbruck Bridge had long served as an essential route for vehicular and railway transport, connecting communities and facilitating efficient travel. However, due to its aging structure and the need for modernization, it became imperative to either replace or significantly update the bridge. The project involved the delicate relocation of the bridge as part of its dismantling, a task that required precise planning, extensive coordination, and a substantial investment of time and resources. The planning stage of the Rosbruck Bridge relocation began well in advance of the actual physical work. The bridge's location over an active SNCF railway line presented a unique challenge, requiring meticulous measures to ensure the safety of both workers and nearby infrastructure. Engineers and project planners worked closely with the French National Railway Company, SNCF, to devise a strategy that would accommodate the relocation without endangering or excessively disrupting the rail line's regular operations. Given the bridge's strategic importance and its position over a critical railway line, the planning process included numerous safety protocols, including securing proper permits and carefully scheduling around other railway activities. To facilitate the bridge's removal and eventual dismantling, the SNCF line directly underneath had to be temporarily shut down, a step that required precise timing to minimize disruptions to rail services. The physical relocation of the Rosbruck Bridge was a feat that unfolded over an intense 72-hour period. To initiate this phase, the SNCF line beneath the bridge was closed, and teams began by removing the railway tracks and the overhead electrical cables. This step was essential, not only to allow room for the bridge's relocation, but also to ensure the safety of the underlying rail infrastructure. With these elements removed, workers could proceed with the heavy lifting required to shift the bridge structure from its original position. The relocation process demanded specialized machinery and expert handling. As the bridge was moved inch by inch from its long-standing position, the operation took place as a synchronized effort, with cranes, hydraulic jacks, and other heavy-duty equipment working in unison to lift and guide the bridge. The precision required at each stage of movement highlighted the engineering prowess involved in such projects, as even the slightest miscalculation could have resulted in structural instability or damage to the bridge and nearby infrastructure. During the 72-hour process, workers operated in rotating shifts to maintain a continuous workflow, ensuring that the bridge was successfully relocated within the tight time frame. The successful relocation of the Rosbruck Bridge marks a significant milestone in the broader project of dismantling and replacing the aging structure. The Caversham Road Rail Bridge replacement in Reading was a major engineering project focused on enhancing rail infrastructure and future-proofing the area for increased capacity. This project was essential to support the planned Crossrail extension to Reading, which was set to begin service in 2019. Led by Network Rail and BAM Nuttall, the bridge replacement aimed to replace 4 outdated bridges with a new, modern structure capable of handling the demands of increased rail traffic. The centerpiece of the project was a new 1,000-ton steel and concrete deck, which was designed and constructed off-site to reduce disruption to traffic and rail services. By assembling the bridge in a controlled environment away from the busy rail corridor, engineers could ensure quality and precision. Once completed, the massive deck was transported to the site and carefully slotted into position over Caversham Road, minimizing the need for prolonged road closures or service interruptions. This approach exemplified innovative bridge construction techniques, leveraging modular construction and prefabrication to streamline the process. Replacing the old bridges was critical for accommodating larger and more frequent trains, which would be introduced as part of the Crossrail expansion. The new bridge structure was designed not only for enhanced capacity, but also for longevity and resilience, ensuring that it would serve the region for decades to come. Moreover, this project underscored Network Rail and BAM Nuttall's commitment to modernizing the rail network while prioritizing safety and efficiency. This bridge replacement was part of a broader series of infrastructure upgrades across the Great Western Main Line, reflecting the wider goals of the Crossrail initiative to improve connectivity between London and surrounding regions. By enhancing the rail link to Reading, the project aimed to reduce travel times, improve passenger experiences, and support economic growth in the Thames Valley and beyond. The demolition and reconstruction of the Oldham Road Railway Bridge in Ashton under Lyne in 2014 marked a significant milestone in the region's railway modernization efforts. This project was part of the broader electrification initiative across northern England's railways, aimed at updating the infrastructure to accommodate electric trains. This upgrade promised benefits including enhanced speed, reduced travel times, and lower emissions. The Oldham Road Bridge, which carried the railway line over a busy road in Ashton under Lyne, needed to be demolished and rebuilt at a higher elevation to accommodate the overhead wires required for the electrification. The Oldham Road Bridge was a long-standing structure on the railway line, running through Ashton under Lyne, a town in Greater Manchester. Originally built for traditional rail lines, the bridge had become an impediment to the expansion and modernization plans necessary for electrifying this railway route. Electrification requires overhead lines that provide power to the trains, and these lines need clearance to ensure they can be safely installed without posing a risk to other vehicles or pedestrians. The old bridge, however, did not have the necessary height to safely accommodate these lines, and thus a replacement was required. This bridge, carrying a crucial link on the railway line that connected Manchester with surrounding towns and cities, was a critical infrastructure component. In light of the rapidly increasing demand for efficient and sustainable rail transport in the area, the bridge replacement was a necessary step for Network Rail, which oversaw the project. The demolition and subsequent rebuilding of the bridge was projected to enable higher frequency of services, more reliable trains, and an overall modernized network. The demolition of the Oldham Road Railway Bridge was a complex process that required careful planning and execution. Scheduled to minimize disruption as much as possible, the demolition was conducted over a series of closures in 2014. Given that the bridge was located on a busy route, the project team worked to ensure safety and minimize the impact on both road traffic and rail services. Demolition involved carefully dismantling the old bridge structure, which included removing large sections of steel and concrete. Specialized equipment, including cranes and hydraulic tools, was utilized to safely bring down the bridge without damaging surrounding areas or the railway lines. The process required skilled engineers and workers to precisely execute each step to avoid accidental damage and ensure the bridge could be safely reconstructed. As with most demolition projects of this scale, there were logistical challenges. Road closures were coordinated to reduce disruptions to the public. Although drivers and commuters in Ashton under Lyne experienced delays and detours throughout the process, pedestrian access was also affected, as construction zones were cordoned off for safety. Despite these challenges, the demolition was completed on schedule, setting the stage for the construction of the new bridge. Following the demolition, the focus shifted to building the new, higher bridge to accommodate the electrification infrastructure. This replacement bridge was designed to be more robust and slightly elevated compared to the old structure, ensuring the necessary clearance for overhead power lines. Network Rail and their construction partners worked around the clock to construct the new bridge, aiming to complete the project swiftly to minimize prolonged disruptions. The new bridge was designed with modern materials and engineering techniques to ensure durability and longevity. A key component of the design was ensuring that it could handle increased train traffic and heavier trains, in line with future projections for the rail network. Additionally, the bridge's structure was optimized to reduce maintenance requirements, which is critical for high-traffic areas that need to minimize the impact of future repairs on rail and road users. During the rebuilding phase, engineers placed a high priority on ensuring the safety of the structure for both rail and road users. The new bridge was engineered to withstand the stress of frequent rail services, as well as vehicular traffic below. Once the main components of the bridge were installed, the team moved on to finalize the details, including rail track alignment, installation of electrification fixtures, and surfacing work. The reconstruction of the Oldham Road Bridge was an integral part of the Northern Hub Rail Improvement Project, a major endeavor aimed at enhancing the overall efficiency and capacity of rail services across northern England. Electrifying this line brought numerous benefits, both locally and across the region. Electric trains are generally more reliable, with fewer mechanical issues than their diesel counterparts, and they offer a quieter, smoother ride for passengers. From an environmental perspective, the shift to electric trains marked a significant reduction in carbon emissions. Electric trains produce no on-site emissions, making them a cleaner alternative to diesel. This shift aligned with the UK government's commitment to reducing carbon footprints in public transportation and promoting sustainable infrastructure projects. For the local community, the bridge reconstruction meant a safer, modernized infrastructure that would support better rail services. With electrification in place, rail services through Ashton under Lyne became faster and more frequent, benefiting both daily commuters and occasional travelers. Furthermore, the project created temporary construction jobs and involved local contractors, contributing to the local economy. Despite the project's success, it was not without challenges. The need for road and rail closures was a source of frustration for residents and businesses, as it disrupted both daily life and commerce. Network Rail took measures to address these concerns by providing regular updates, coordinating with local authorities, and implementing detour plans. Another challenge was coordinating the project timeline to align with other infrastructure improvements in the region, including other bridge reconstructions and track upgrades. Given the tight schedules and interdependencies with other projects, Network Rail and its partners faced pressures to deliver the bridge reconstruction on time and within budget.